Welcome back to part 4, underground rock excavation. We will continue with learning the failure mechanisms of underground excavation. In this session, we will learn what types of failure will occur, when they will occur, and what are the main cause of such failure. From there, we will learn later how to prevent or control those failures in terms of support and excavation optimization. Here, I have summarized the failures you would expect in underground excavations and associated rock and ground characteristics. For tunnels and caverns excavation, the common failure types are 1. General failure in the form of raveling and the running down of the unsupported, highly fractured or highly weathered ground. 2. Block and wedge failure or sliding down from roof or side walls, along joints and the fractures in the rock masses. 3. Spalling and rock burst at excavation's face, and rock fracturing at the corners due to high stress or stress concentration. 4. Large convergence and deformation, when the surrounding rock is highly deformable and swelling. For caving mining, failure by gravity fall of fractured rock mass is controlled. We'll have to deal with this type of designed failure differently. Ground settlement and subsidence is generally associated with over-excavation or caving. It may lead to failure of structures at the ground. We will elaborate each failure type in details in the coming slides. Genuine failure in the form of running and the raveling occurs in granular and the loose materials such as highly fractured, highly weathered, poor, and loose rock masses. The surrounding earth collapses into the opening by raveling. With groundwater, raveling can turn into running and flowing. Usually, tunneling in this type of ground are well supported to prevent such a failure. The support must be in place immediately after the excavation. For example, using the shield tunneling machine so that the circumference of the excavated tunnel is always supported. If in really unstable ground, excavation face can also be supported during excavation. For underground excavations in generally competent and good solid rocks at a shallow and moderate depths, as for most of the tunnels and caverns, failure of surrounding rock mass around the tunnel is by falling or sliding of rock blocks and wedges that are formed by intersecting joints as illustrated by the drawing here. This type of failure is termed as structurally controlled failure, as the blocks and the wedges are controlled by the discontinuities structures, and sliding is along those discontinuity structures. Here are examples of structurally controlled failure. The one on the left is a tunnel aft block falling. The tunnel actually has an arch roof, but the tunnel profile you see now is no longer arch, but shaped by the joints. Those loose rock blocks and the wedges at the tunnel roof fall down. The tunnel roof is now unstable because the blocks are now interlocked and are not able to fall. On the right photo, you can see a wedge just fall down from the roof with broken pieces on the ground. Again, those failures occur because of existence of joints and the fractures. The failure is a structurally controlled failure. When tunnels and mines are at great depths and under very high stress, rock can suffer spalling and popping breaking at circumferences or at excavation phase. When such stress-induced failure become large scale, we have rock burst. High stress is primarily due to high in situ stress associated with great depths or tectonic stress. Localized stress concentration may build up at the corners and at intersections that may become high enough to cause fracturing and the breaking of rock at those locations. As rocks are generally brittle, so spalling and rock burst usually associated with sudden failure and microseismicity. The photo on the left here shows spalling failure in a deep hard rock mine. You should be able to note the thin rock flakes in front of the miner. This is a similar failure mode as disk fracturing in rock cores when drilling at great depths, by the photo on the right. Spalling and rock burst are stress-induced failure and occur usually at great depths over 1,000 meters. Another common failure form is shown by large deformation and the convergence of the excavated opening. We use a term of squeezing, and the surrounding rock is squeezed into tunnel, often damage the support and causing excessive convergence. This type of failure is usually occurring in weak or poor quality rock masses under relatively high stresses. Anisotropic squeezing can also occur in rocks with anisotropic properties, for example, in schists. Large shear displacements along schistosity can lead to squeezing in that direction. Again, here is an example of squeezing. You can see clearly the amount of convergence of the tunnel and the damage of the original steel ribs. Normally, the two key factors leading to squeezing are weak or poor rock mass and the relative high in-situ stress. Squeezing can also due to the swelling nature of some rocks containing swelling minerals. In this case, the large deformation is caused by swelling of the material when exposed to wetting. While in construction, our target is to build stable tunnels and caverns with appropriate rock support. In mining, especially in caving mining, the target is to allow all rocks to fail and to collapse, but in a controlled manner. Here, fractured rock mass are failed by gravity in the caving process. The failure is primarily structurally controlled failure, as rock blocks formed by joints and the fractures in the rock masses, falling down and collapse progressively. Instead of analyzing stability in caving, we are analyzing capability to design caving. We will learn later on caving mining and the capability assessment. Here is an illustration on how capability is related to rock mass quality. As you can see that caving can happen at a low IMR, that is poor rock mass quality. Caving is of course also affected by the caving dimension. As we would expect, larger dimension lead to higher possibility of failure, i.e. caving. It is interesting to note that we can actually analyze stability and the capability using the same parameters, the rock mass quality. As you can see on the figure here, the opening is stable at a higher IMR and a smaller dimension. Let us recapture what we have learned on failure mechanism. We now know that the two factors causing underground excavation failure are rock mass quality and the stress level. Those two factors not only cause failure, but also define failure modes of underground excavations in rock, whether to be stress-induced or structurally controlled. The table below is a simplified diagram showing the effects of stress and rock mass quality on failure modes. For rock mass of generally good quality, the possible failure are block falling and sliding, controlled by joints at a low stress level. At a high stress, spalling or even bursting may occur. On the other hand, for poor and weak rock mass, we will have general failure at a low stress and a squeezing at a high stress. The relationship between failure mode and the rock mass quality can be found in support design. For example, in the Q-based design chart here, we note zone 2 and 3 are bolting for block failure and sliding. In zones 8 and 9, steel ribs and the casting concrete lining are for general failure and squeezing. Stable zone is shown on the low right, and unstable zone or possible collapsing zone is on the upper left. Here, different failure and support to stabilize the potential failure are quantified by rock mass quality Q and excavation dimension. We can also use GSI chart to estimate different potential failure modes. For example, at the low stress level, the two main failure modes are structurally controlled failure and the general failure. The former occurs in blocky and reasonably fair quality rock mass, shown in mocha color. But for poor rock mass, we'll have general failure, indicated by gray. For high quality rock mass, we would expect stable excavation, which is in green. With stress increase to moderate level, it helps to stabilize the excavation. Therefore, we have more stable zone. For poor rock mass, structural controlled failure and the general failure will still happen, and they are not much influenced by stress. When stress becomes high, we are going to face squeezing in poor and weak rock mass, shown in purple, while high stress may help to stabilize the excavation for good and the solid rock mass. For fair quality rock mass, small blocks will suffer instability under high stress. This is indicated by large blue zone. When the stress becomes very high, more squeezing is expected for poor and even fair quality rock mass. In addition to small block instability, very high stress may lead to the spalling failure we see in the photo earlier. To the worst extent, rock burst may happen. Again, we have envisaged that the failure of underground excavations in rock are resulted from two major factors: the rock mass quality and the stress level. By summarizing the results from the previous 4 slides on failure modes and GSI, we may end up with this diagram, indicating failure modes zones with stress and the GSI. This diagram here is to serve the purpose of explaining the connection between rock mass failure in underground excavation and the two key factors governing the failure. I hope I have explained clearly the failures you would expect and how they're governed by the rock mass quality and the stress. I'm ending this session now. We'll continue with underground support mechanisms in the coming sessions. Goodbye, and see you at the next session.